Elementary arithmetic relies on symmetry. We define division as multiplication run in reverse. If you divide 10 by 2, you get 5, because 5 times 2 is 10. But replace that denominator with 0, and the system breaks. The operation refuses to resolve backwards, because no number yields 10 when multiplied by 0. Instead of assigning a value to this operation, mathematics universally labels it as undefined. Leaving division by 0 undefined serves as a protective mechanism required to prevent the entire numerical system from collapsing on itself. Division functions algorithmically as repeated subtraction, determining how many times a divisor can be removed from a dividend before reaching 0. Early mechanical machines, like this facet calculator, physically broke down when tasked with this operation. Because subtracting 0 never reduces the starting value, the machine enters an endless, high-speed loop of subtracting nothing until the internal motor is disconnected or the gears seize. In pure algebra, we see the same failure when we test the assumption that 1 divided by 0 equals an unknown value, x. We can rewrite this as its multiplication equivalent, 1 equals 0 times x. Because any number multiplied by 0 is 0, the equation simplifies into a contradiction, 1 equals 0. Accepting this contradiction allows you to manipulate any other number. By adding 1 to both sides of 1 equals 0, you can prove that 2 equals 1. By multiplying both sides, you can prove that 5 equals 0. This destroys the uniqueness of numerical values. If every number equals every other number, quantity loses its meaning, and the entire number system becomes a single, useless point. Calculus attempts to find a solution through limits, dividing by numbers that get progressively closer to 0 rather than 0 itself. As the denominator shrinks through increasingly smaller positive numbers, the resulting value accelerates exponentially toward positive infinity. However, approaching 0 using increasingly smaller negative numbers forces the result to accelerate toward negative infinity instead. Because the operation violently tears in two mutually exclusive directions depending on the approach, it is impossible to define it as a single static value like infinity. While dividing a non-zero number by 0 yields no valid answers, dividing 0 by 0 creates a different mathematical anomaly. Reversing the logic for 0 divided by 0 requires a number that equals 0 when multiplied by 0. In this case, every number in existence satisfies the requirement. The equation 0 equals 0 times x remains true no matter what value we assign to x. This is the critical distinction. A non-zero number divided by 0 is undefined because there are 0 solutions, but 0 divided by 0 is indeterminate because there are infinitely many. If we refuse to accept an undefined result and decide to rewrite the core laws of arithmetic to force an answer, the system must be entirely rebuilt. Wheel theory provides this architecture. It is a specialized geometric structure that extends standard arithmetic to safely contain division by 0. This structure bends the infinite real number line into a closed loop, introducing a central element called nullity to handle the indeterminate 0 divided by 0 state. Nullity acts as an absolute mathematical sink. Any standard arithmetic operation is instantly absorbed, returning the nullity symbol. Giving division by 0 a definitive value is possible, but it requires sacrificing the standard rules of addition and subtraction that govern our daily calculations. This fundamental fragility is why modern computer processors are hard-coded to intercept zero division errors before they can execute. Early microprocessors, like the Intel 4004, lacked the physical architecture to handle this mathematical paradox internally. Whether running inside silicon chips or existing in theoretical logic, a functioning system cannot tolerate an operation that erases its own rules. Leaving division by 0 undefined is a protective necessity designed to keep the entire universe of numbers intact.